I'm Hung this assessment, and today we're going to present about our assignment 3, and this is our ID. So now our first task to allow for 3 subnets, each with our host will be using 3/29 subnet mask, which will provide each with 6 usable IP address. For the 1 subnet with a host, we'll be using the /28 subnet mask, which will provide 14 usable IP address. So by doing this, we're sure that we're following the requirements of least and minimal subnet range. So now onto our IP addressing scheme. We'll be using the base IP range from 192.168.1.0/24 to .255/24. And for this, we'll be assigning IP address to the 3/29 subnet first and the /28 subnet at the end. So first in subnet A, the IP range will be from 192.168.1.0 to 192.168.1.7. For subnet B, it will be from 192.168.1.8 to 192.168.1.15. For subnet A will be from 192.168.1.16 to 192.168.1.23. And for subnet B, which is a /28 subnet, would be from 192.168.1.32 to 192.168.1.47. So the reason for why the IP address range from 192.168.1.24 to 192.168.1.31 is in use is because we're setting the IP address to the /28 subnet at the end. And because of this, 192.168.1.24 is a valid starting point for /28 subnet. A valid starting point would have to be a multiple of 16, like .0, .16, or .32. And please note that those IP address range will not be gone to waste. As in task 2, we'll be using them to provide further subnetting to allow for inter-VLAN communications. Now onto the topology, we will have the one centralized router which will handling the layer 3 traffic between hosts from different subnets. Each subnet will have their own switch to handle layer 2 communication between hosts in the same subnets. And also the router will be assigned with different router interface will be assigned with different IP address and subnet masks, in which they will act as the default gateway for their respective subnets. So now I'll demonstrate the working of our topology by trying to ping some device from different subnet. As you can see here, I've already tried to ping some and they're all successful. Now I'll try to ping some more. As you can see, this one fails due to ARPA process and this one is successful. Now moving on to task 2, we'll be assigning 2 VLANs, VLAN 10 and VLAN 22 subnet A. To allow for inter-VLAN communication, we'll be using a router on stick configuration where each VLAN will have their own subnet range. And because of this, the IP addressing scheme for task 2 we'll have to change a little bit compared to task 1. So please note that from task 2 onwards, we'll be using this new topology with the new IP addressing scheme. So now continue with the physical interface of the router that's connected to the switch of these 2 VLANs. It will be divided into 2 logical subinterfaces, each associated with a specific VLAN by using the encapsulation.1q command. These subinterfaces are also assigned with IP address of their related VLAN subnet, in which they will act as the default gateway for that specific VLAN. We'll also have to configure a trunk link between the switch and the router to carry out the data traffic from both of the VLANs. So now to demonstrate for intra-VLAN communication, I'll try to disable the router interface between the router and the switch that's connected to the 2 VLANs. So now when I try to ping from hosts within the same VLAN, as you can see, they're all successful. But when I try to ping from hosts from different VLANs, they will fail. So the reason behind this is due to how VLAN works for intra-VLAN traffic. So take this as an example. When I try to ping from this host to this host, which are both in VLAN 10, firstly, the frames will be created. It will then get transmitted to the switch. Here, the switch will identify which VLAN that frame belongs to by checking the VLANs assigned to the ingress port. In this case, it will be VLAN 10. It will then look up its MAC address table for the destination MAC address found in the frame. And here, 2 scenarios could happen. Firstly, if the MAC address found is within the same VLAN, the switch will then forward it to the associated egress port, which will transmit the frames to the destination. Otherwise, if the MAC address is also found in the MAC address table, however, it's not within the same VLAN, then that frame will get dropped, explaining the reason behind why hosts from different VLANs cannot communicate. So now to demonstrate inter-VLAN communication, I will turn this router interface back on. Now I will try to ping between hosts from different VLANs to each other. And as you can see, the ping is successful, showing that hosts from different VLANs can now communicate to each other. So how this works is that when this host tries to communicate to this host, this will first create a frame, and it will try to send it to the default gateway in the router because it's trying to communicate to another host in a different subnet. So the switch will receive this frame, and at the short link, it will attach a VLAN tag to that frame to identify which VLAN that frame belongs to, and then send the frame to the router physical interface. At the router, it will use that VLAN tag to direct the frames to the associated subinterface of that VLAN to perform layer 3 routing. The router will perform layer 3 routing, and then it will rewrite the frame with a new destination and source MAC address, sends it back to the switch. The switch will remove the VLAN tag and forward the frame to the correct destination host using the destination MAC address in the frame.
Okay, so next, coming to task 3, I'm going to show you how to create ARB tables in Cisco Packet Tracer. So here I show you the ARB map in the router. I have the 1.17 here for and 1.17, 1.21 and 1.34, which is these two computer. Now I try to delete the ARB using the command from the command prompt. I delete it. See, no ARB entries file. And I also delete it on the router. But the problem is they're still here, because actually Cisco Packet Tracer is a little bit too smart that we remember on the ARB until we close the app. So actually we can still bring them together even though I have deleted the ARB. Now to demonstrate how layer 2 and layer 3 address change in the ingress points across all network. Here I have BC1, which is the 1.18 in the subnet B, and the BC2, which is the 1.26 in subnet C, and the package leave the BC1 is sent to the default gateway, which is the 1.17. Here it's continued to be sent, and after the router receive it, and the packet is sent to the default gateway, the ingress point. At this point, the layer 2 frame has the BC1 MAC as the resource and the router's MAC on the gigabit Ethernet 0/7 at the destination. The layer 3 packet carries source IP 1.18 and destination 1.26. When the router receives the packet, it removes the layer 2 header, check the IP, and forward it to the gigabit Ethernet 0/8, which is the egress point. It then rebuilds the layer 2 frame with the gigabit Ethernet 0/8 MAC at the source and the BC2 MAC at the destination. The IP address stays the same through. Router change layer 2 address at each hop while keeping layer 3 address constant. For VLAN 10 and 20 on the trunk interface gigabit Ethernet 0/6, the sub-interface for 6.10 and 6.20, the same rule applies. Only MAC address change as the packet moves between VLAN. IP address remain unchanged. When the ping returns from the BC2 to the BC1, it goes through the same route but in the reverse order. Coming up next to task 4, I've added a web server and I have enabled the HTTP service here. And for the DNS, I have set it to point to the 1.42, and I have also added a record for cisco.com. Here's how I try to access it from many computers, like here. I've saved with the IP address, and with this computer, I've saved with the domain name. And it's still successful. Then I'll try to ping it using the ICMP packet. Here I ping it from every subnet and every VLAN so that you can see it's successful. Next, I'm going to show you how the step-by-step HTTP request journey from the PC to the web server. And first, inside the computer, you have to reach the application layer. It's when the user opens the web server and enter the address of the web server. Next, to the transport layer, the TCP will create a segment and it adds the source port and destination port, usually 80 for HTTP, and also it adds a sequence for reliability. Then for the network layer, it will add a source IP at 1.3 and a destination IP of 1.42, and see the destination outside the subnet. It will use the default gateway to pass it through. Next, we come to the data link layer, which is layer 2. Since the net hop is the default gateway, the PC will check for the ARB request for the MAC address of 1.1. But since the ARB have been checked before in the earlier step, it don't need to do it anymore. And finally, it will go through layer 1 which the data will be sent electrical signals through the fiber wire to access the board of the switch. Next, after the computer has sent the package, the access board from the switch receives an untagged frame and is added to the VLAN 10 internally. Then it will forward the frame to a trunk board, maintaining the VLAN tag, and it sends the frame to the router. The router then receives a trunk VLAN 10 frame on gigabit 0/6, and the sub-interface 0/6.10 is configured with IP 1.1 and handle the VLAN traffic. The router then removes the VLAN tag, inspect the IP header, and see that the IP destination is 1.32, and now in the scene submit with the PC, it will look up in the routing table and find a route to that destination. Then it will be prepared to forward the packet via appropriate sub-interface for the gigabit 0/9 and the IPS default gateway of 1.33. And encapsulation happen again. Then the new Ethernet frame will be created with the source MAC of the router and the destination MAC of the web server gateway. Now, at that web server, it will go through 7 layers of RSI, with the physical will receive and convert the bit into the frame. Data links layer will have the MAC address checked and the frame is set. For network address, the IP is checked and the destination IP will matches with the server. Then the transport layer will have the TCP header placed and the port 80 recognizes connection will be accepted by the server. Then the session will establish at the sessions layer and the data will be decoded with YouTube. At the application layer, the web server will receive an HTTP GET request. Then the web server will try to respond to the PC. As it sends an HTTP response to the 1.3, use the default gateway 1.33. Then the frame will send to the switch, to the router, and it will have the routing decision made there. Then the router tag it for VLAN 10, send via trunk port to the switch, to the access port to the PC. Then the PC receives and the encapsulates response back to the router.